Hello.
Hello.
Hello. So I'm Charlie. So I run this group.
Hello.
Hello.
Yeah. Hey Dara and hey Jagadish.
Yeah, that's me, Jagdish. Yeah,
Cool. Yeah, we'll give some people time to join and then we'll kick things off properly.
great.
Uh, yeah. But as an intro, I guess so at the moment we're working on this static yaw misalignment challenge
Yeah.
and trying to solve that using open tools like Renku and OpenOA. So Renku is this data science space, and hopefully we'll have a an example from one of the team on how they've set things up. And then OpenOA is this tool that NREL, which has been rebranded recently as National Laboratory of the Rockies to
Okay.
remove the reference to renewables in the US. Uh, they've got this open tool that includes, as part of the analysis, the ability to, well, calculate static yaw misalignments.
Yeah.
Yeah.
What will be your, like, I will wait for your presentation. So I'm quite keen to know about the data you use on this and how we can, to have some experience in the Metocean data collection side. So
Yep.
always see this possibility of integrating that data into this alignment, mainly on the floating side, floating WTG. So it'd be
Yep.
good to see what you're recommending.
Yeah, cool. Yeah. So with this challenge, then we're using a data set from effectively a small experimental turbine that
Mm.
University have. The advantage of that was that we could get, well, higher frequency data for one. Uh, so like 1 hertz-ish. And
Oh, right.
then we were also able to apply misalignments to the turbine and know what those misalignments, at least in the parameters, what was applied. So, with a commercial machine, companies that own those turbines are less willing to make changes that will, well, first off, reduce production, but second off, might damage the turbines. So this was like a test turbine where we could actually experiment and try things out.
Right, yeah. And what is this location?
It's in Switzerland,
Okay, on
uh,
the land.
on land. Yep, yeah, yeah. And if you are looking for like open data from operational wind farms, they're all onshore, but there's free sites now with open data, open SCADA data.
Yeah,
So Kelmarsh and Penmanshil that Yubico own. Uh, that's got now, I think, like 5 years of data for each of those two sites. And then there's also Hill of Towie as well, which Res have managed to release and tricks the owner of those sites. But yeah, if you're interested in looking at SCADA data in general from wind farms, then those are some good data sets.
that's good. Yeah, my experience mainly is the floating wind side. So, and I'm quite keen to seek some of these data set, which
Yeah.
is very, which not have, there is no much floating wind. It's all been fixed at like offshore winds, which is like, which we can understand with the cost perspective on this.
Yeah.
And see what you can suggest. Yeah.
Yeah. Well, that's good. Florian, do you know if Yuri's joining? Because I think he was hopefully going to present something.
No clue if Fear is joining.
No
I,
idea.
I, I also don't know if Sarah's joining. I don't know what she wrote you.
Yeah. Let me double check.
Oh, Dara, do you know? Did Sarah say something?
Uh, Not sure really. Yeah.
Okay.
Yeah, well, while that's happening, I can share my screen just to show where the challenge is. It's to So hopefully you've all accessed this anyway. So it's the WeDoWind site, and then there's Open Data Exploration, which is this group call, and then the most recent challenge is listed here. So if you click on that, you can read about the challenge, and then also you can follow the instructions to set up uh, set up an analysis on Renku, and also register for the challenge as well. But I'll let you do that in your own time. And then also here we have previous challenge results. So operational energy yield analysis, static yaw misalignments, first round, and then predicting the wind speed. And if you look in the open data sets, this is for you, Jagadish. There's a list of various data sets that might be of interest. Okay, well, while that's happening, while I'm waiting for a response from Sarah, I'll just show everyone the Renku platform, and I can run through what I've done recently with the data and challenge. So on Renku, there was a link that I followed. There's this repository. Oh, let me log in. It's two-factor authentication is always causing trouble. So yeah, if you sign up for Renku, you can do it either with your email address, or I think preferably GitHub if you've got GitHub set up. Use your GitHub account. And then there's this template set up, and you can create your own copy. So it'll say create your own copy here. And then I've done that, so I can go to my own copy. The one I'm going to use though to show you what I've been up to is in this one. And all I've done in addition is add my GitHub repository, which, let's see if I click through. So I've got a very basic analysis attached, and this is in my GitHub account. So what that means is if you want to see my code, you can look on GitHub, and in fact, you could add to Renku that repository, and you'll be able to see what uploads and use my code. Let's just resume. I realize I've started this. Shall we do a quick round of intros before I continue further? I think this is probably it now. So I'll start. Yeah, I'm Charlie. I run this group. I work for Nuvian Infrastructure, which is a owner of wind, solar, and battery storage projects. And my role is kind of focused on performance of those assets and also data and data systems. So how we use data from our assets to, for instance, improve performance. And then I set up this group a few years ago because I released some data to Cubico datasets, and I wanted people to be able to use that data and to be able to see what people were using that data for. So the idea was to run some challenges or just discuss the data sets so that more people could get involved. And then I've continued to run the group, and one of the focuses has been on operational performance of wind turbines. So in this case, static yaw misalignments, and can we identify them from data? And then, assuming we can, then we can correct for them and improve turbine performance. So I'll run down the participant list, and that puts Dara in second place. So do you want to do a quick intro?
Yeah, sure, Charlie. So I'm Dara. I'm a research assistant at OST at the Eastern Switzerland University of Applied Science, and my mainly focus is on the aerodynamic modeling. I have a background. I did my PhD in wind turbine wakes, so quite familiar with the fluid dynamics part of the wind turbine flows. And yeah, it's the first time I'm participating actually in challenges on B2Win, so I'm quite excited to understand how all the setup and everything will work.
Yeah, cool. Thanks, Dara. Florian, you're next.
Yeah, hi, I'm Florian. Yeah, I work with Dara and then Sarah actually at the Eastern Switzerland University. We set up these challenges with Charlie. Now I don't know how many you have done already. Yeah, Charlie tests his stuff, the data related things, and with this challenge we are testing a data science platform, Rainku, which is my part of the work. So I've set up this environment, provided folders, data and scripts. So I'm just very interested in this meeting. If anyone has tried to set it up already, wants to set it up, wants to test it as part of this challenge, or not. And if so, if not, why not? There might be good reasons. But yeah, that's my task in this challenge to provide this data science platform access.
Yeah, thanks, Florian. And then Ganesh, would you like to do a quick intro?
Yep. Can you guys hear me?
Yep.
Yeah. So I think I have some challenge, but yeah, let me see. You guys can hear me clearly, right?
Yep. Can
Yeah.
see you as well. So camera's working as well.
Okay. So I'm basically mechanical engineering graduate. I was with GE for like 18 years. Did started with gearbox or gear engineer, and then went on to do the system engineering. We started from 1 megawatt machine, and when I came out, we were doing 6 megawatt onshore, and I had little bit experience on offshore for 14 megawatt. Did couple of various projects starting from India, China, US, Europe. So most of my focus was on system engineering, building the platform which can be used globally, scaled globally. What I'm looking at from this event is to get into the data analytics and AI aspects of wind turbine performance, management, improvement. Yeah, so that's brief about me. So my expertise is mainly on the system engineering aspect. I'm very new to data, trying to learn, but somehow not able to get into it.
Well, this will be a good test of that data analysis
Yeah,
skill. So a good opportunity to learn.
yeah.
Yeah, and I
And
mean,
I will be, sorry to interrupt, and I will be looking to work with someone like you or anyone who has already a data background, and then my learning journey can be faster. So I I have a lot of field as well as uh, field experience as well as engineering experience, and we have solved a lot of challenges when it comes to yaw misalignment. And in fact, I was part of discussions where customer was charging GE because of some of the issues on the yaw misalignment. So I know a lot of things, how uh, why it happens, how it happens, and how the data if you have a good backup of data, that can help IPPs as well as OEM to improve the product performance.
Yep. Yeah, that sounds good. Yeah, it's always good to get some people with site experience into data groups as well to feed the information both ways.
Yeah,
Yep.
thank you.
Cool. Thanks, Ganesh. And then Jagadish, would you like to do a quick intro to the group?
Yeah, thanks, Tol. So myself, an oceanographer, basically worked in the marine environment, got quite experience in marine survey, and I was involved with floating offshore wind for this ScotWind and INTOP projects. So quite seriously involved for last 5 years, and now I'm doing things by myself. So I'm just trying right now working as a consultant on this. So looking forward to learn more from here rather than contribute because I have a bit limited experience on same as Ganesh highlighted data analysis and all. I'll be more of measurement and data collection perspective. So that's me. Thanks.
Yeah, very cool. Yeah, I think then this is a good project to work on. You'll get access to data.
Yeah,
You'll be able
the terms are pretty challenging for offshore wind as well. So these yo and all those things are pretty vital to understand. So it's good to learn, well, so that we can implement on the measurement methodologies as well. So
Yep.
basically we need to understand what this data use. Otherwise everybody asks why do you collect this data? So yeah. So, thanks.
Yeah, that sounds good. And fingers crossed with the Renku platform that it will remove some of those initial like blockers or boundaries that you have to cross, because the platform should make it very simple to start up and get going, kind of thing.
Okay.
At least that's the plan. Cool. Then Jingu.
Yeah.
So yeah.
Hi, everyone. Thank you so much for including me. So I am fairly new to this group. I actually just found out about this yesterday from Sarah, and she said that there's like a monthly meeting, so I thought I'll come and check it out. So come from a data scientist background, but did my master's in industrial engineering. So like mechanical engineering, just like next door industrial engineering. So we did some of the system engineering, some of the physics courses together, but never really like went into the wind turbine field. So right now working for a robotic company that developing specialized sensors for wind turbine inspections. So then the question for the company is like, okay, like what other data sets are there for the wind turbine? Like how can we use our data and how can we kind of merge our data together? So that's where I am trying to learn about the wind sector, also trying to learn about the data science problems within this sector.
Oh, very cool. Yeah, that sounds good. And nice to have you in the group. And well done on managing to join so quickly.
Thank you.
Yeah. Okay, can you just say your name, just so I get the pronunciation right?
Oh, me is Jing.
Jing.
Yeah,
Good.
just think about Jingle Bell. So it's Christmas.
It's going on to Christmas. Yeah, perfect
Yes.
timing. Cool. Thank you. Okay. So I'll just share my screen and show you the Renku environment. And this one's very similar to the one you'll see when you set it up, but with one slight difference. There's my repository here with my basic analysis in it. So with this, it's a Python Jupyter notebook, which is very good for data science. Lots of data scientists use this. And in fact, we ran a Kaggle challenge last year, and Res ran a Kaggle challenge this year. And in Kaggle, then effectively, Jupyter notebooks are the way that people share the code and results. These first two lines, I've just installed some packages that weren't installed. And then I've tried to run code to have a look at the data and also see if I could identify the static yaw misalignments that we know about. So this bit is importing the libraries, and then we have our data set. So if we go up a level, And in fact, let me open another window with Renku. So the nice thing about Renku is basically you don't need any specialist computing equipment. All you need is your username and password. And then you can very quickly add data sets. So in the template, we've added this data set, which is on Zenodo, which is the data from our wind turbine. So if we click through some description there, and then you can see the data repository here on Zenodo. And the data itself is stored in Parquet format, which is like a compressed data format. Again, very good for analyzing once you set it up in that format. And then as well as adding data sets, we've added a drive. So if you sign up to the challenge on the WeDoWind website, then you'll receive a username and password. Florian, correct me if I get any of this wrong. And then you can save your code to that drive folder. And then here I've also added my, WeDoWind static your ground truth challenge repository, which is on GitHub. And that means when I'm in the environment, I can see all those things. So I've got the turbine data in this folder. I've got my drive, and I've got my repository. So you can see if I open up the data, it's got the same files that you see in Zenodo. So the metadata, test, and train data sets. Go up. And we've got the drive. I am participant number 4, I think. Oh, maybe not. Same false. Oh, you get a participant number, and then you'll be giving rights access to whichever participant ID you are. So yeah, going back to it. So with this analysis, then I've got my path to the data, reading it in using pandas, and then setting the timestamp. So it's actually a timestamp. And then I've resampled the data to 10 minutes initially. So this is so that I can quickly plot it up and see the different signals. We've got a turbine status signal. And I think those are defined in this croissant file. So it's somewhere down here. There we go. We've got the various turbine status codes. And then we also have standard data signals that you get from a turbine. So rotor speed, generator temperature, wind speed, power output, relative wind direction, supply voltage, blade pitch angle, and the all-important one, your offset. So to give context to this challenge, basically turbines should point into the wind to maximize generation. The wind moves around, so the turbine moves around as well to track the wind to continue to maximize generation. But sometimes the turbine has an offset, so it's got a wind vane on the back, which tells it what direction the wind's coming from. It tries to point into the wind, but sometimes there's an offset on that vane. And what that means is the turbine doesn't point directly into the wind. It always tries to point slightly off. And so there's a misalignment between where it would maximize generation and where it is actually pointing. And this is termed as static yaw misalignment or offset or error, because your wind is always moving around, the turbine's trying to track it, but this is like an offset to that tracking target. So it's always like offset slightly and so producing slightly less than it could. So what we're trying to do in this challenge is identify that offset using data from the turbines. The reason we want to do that is on on like operational sites now, if you've got one of these misalignments, then typically you need to find out by installing equipment on the turbine or doing some like manual inspections on the turbines. So for instance, putting a LiDAR onto the top of the turbine to see if there's a misalignment between the direction the turbine's pointing and the wind direction that's coming in. But with that kind of hardware or inspection-driven approach, then it means it's quite costly because you need to go around every single turbine. Whereas if you can identify this through data, then you can very quickly roll out a fix by just adjusting parameters on a turbine. And so increase generation for an asset or assets. So with this turbine, let's just see if I... no, why not? This turbine, we'll see the data in a second. Once it's installed. Yeah, so with this turbine, we've purposefully put in known static yaw offsets. And then the goal of the challenge is to train a model to identify those static yaw offsets based on the rest of the data. And then we've got a test data set where you can then estimate what those offsets would be based on the same channels that are available in the training data set. And then we'll try and compete to make those predictions as accurate as possible. So that's the goal.
I have a question about this.
Yep.
So you said that the offsets currently has to be recorded through the LiDAR or some kind of sensor. So then in this case, right, how are these offsets being collected?
Yeah. So for these offsets, we applied them directly to the turbine. So there's a parameter in the turbine control system
Okay, I see.
where you can basically adjust it. What we don't actually know is if, well, when the parameter for the offset is 0, whether that means the turbine is pointing perfectly into the wind, because we haven't installed a LiDAR or another device to check if there was a yaw misalignment to start off with, a yaw offset to start off with.
Okay. So then, but then normally when you have the turbine running, and if let's say this offset is a parameter that you can observe in the SCADA data, then normally like what is the what's like the normal range? Do you have a range that you observe?
Yeah, so the yaw offset should be close to 0 because that's basically when turbines pointing
Right.
directly into the wind.
Yeah. Right. Yeah.
There are some nuances to that. So sometimes 0 is not actually where you maximize production. Sometimes there is a slight offset because of the physics of the rotor and the like also flow behind hitting the wind vane or wind sensor. That you actually want to apply a slight offset to maximize generation. So you do see on some turbine models that there's always an offset. What you don't know, though, is if that turbine has been set up the exact same way as all other turbines and in the perfect mode. So what we're trying to do is say, well, at the moment, that parameter is 0, but should it be adjusted to improve generation further?
Okay.
Yeah, hopefully that made sense. So maybe I'll just show.
Then I think another question kind of on this is that like how many turbines there are in this data sets?
Yeah, so in this data set, there's only one wind turbine.
Okay.
Yeah, so it's fairly simple. And here you can see, so this is the training data set. You can see what the offset applied was at various periods of time. So it started at 0. I'm not quite sure why there's a big data gap. Maybe that's part of our test data set. But then you can see that we applied an offset of 6 degrees, then a 4 degrees, and then back up to 6 degrees again. And what we want to be able to do is predict these values or these changes. Because then on a turbine where we don't know these offsets, we can identify them and so correct for them.
So then the problem is kind of like on the data, on scatter data, you observe 0, but then actually the offset is maybe 2, 3, and you just don't know yet.
Yep, yeah, that's it. Yep. Yep. Maybe I'll just show. Alongside this, what did they call it? Relative wind direction. Something still running. Stop. Yeah. So here we've got the relative wind direction. It's 10-minute basis. That's why it looks so noisy when we've got mobs along the bottom axis. So this is where the turbine is trying to point into the wind, but the wind's constantly moving around. So you can see here it's actually varying a lot according to the sensor, from like -50 to +50 degrees. So on a 10-minute basis, the turbine is not pointing perfectly into the wind, but that's normal. That's expected. The thing we're trying to identify is where the turbine's trying to point slightly off into the wind. So there's a lot of if the wind wasn't moving around, then this should be 0 for the bit in January, 0 for the bit April to June. It will still read 0 for the other periods here because the sensor is adjusted to still try and point into where it thinks it's trying to point into the wind. So the relative misalignment would still be 0 in this signal. But we know there's an offset, so you're losing generation. Does that make sense? Maybe. So
And the question is, why are these variables selected? So like the data that you included, I think that in the data set, why did you choose these variables?
Yeah, so these are the standards control variables from a turbine. So they're the ones we expect to impact on your offset signal, or rather be useful in determining that your offset. So like the key ones for OpenOA's methodology for calculating yaw misalignments, key variables being wind speed and power output, and then also relative wind direction. So we've got those three. When you look at the control of a turbine, then generator speed or rotor speed, they should be the same, just with a multiplication factor. But they're useful to see how the turbine is controlled, and then also blade pitch on control of the turbine. So if we look at the power curve here, then turbines are always rated to a certain power output, in this case 6.7, 6.6 kilowatts. And to maintain power output at higher wind speeds, then you end up pitching the blades. So we could do that plot as well. Good. And what did we say is blade pitch. So points up here are where the turbine is basically off, it's in idling mode. And then here is where the turbine tries to start up. So it like pitches the blades down to 40 degrees or so. And then as your wind speed increases, it then goes towards fine pitch, which is where production is maximized. And then you start pitching to reduce. Actually, it start pitches quite early. But you start pitching to control the power output of your turbine so that you don't go above the rate of power of the machine. Typically, though, you're not controlling the turbine using the wind speed measurement. So what you normally have is what's generate speed. So the way you typically control a turbine is, well, it's one of two, but they'll look the same way because they kind of multiply. So typically you control the turbine so that it doesn't go above a certain speed by pitching or above a certain power by pitching. So that's where you get the vertical lines for where we're pitching the turbine. Yeah. Done. So initially so SCADA data from like industrial machines is typically on a 10-minute basis. So you get 10-minute averages, means, max, standard deviations. So that's why I initially pre-sampled to 10 minutes. The power curve, this is always the first thing you look at to see how a turbine's operating. And what I've done is color-coded the points based on the yaw offsets, so these offsets. And what you expect to see is where you've got your offsets, so the yellow points, you get reduced power output compared to the average. Make it a little darker. And that does seem to be like at first glance happening. So near the power curve here, then it looks like the yellow dots are slightly to the right of the like other points, which means the turbine is producing less than it otherwise could. So as a first glance, that suggests to me that you might be able to identify the yaw offset based on, well, wind speed and power from the turbines. I've then tried the same again, but with 1 minute sampling, so that I've got lots more data points. And then I've done some filtering as well. So I've removed any data points where the power output's less than 6 or greater than 0.3, and where the wind speed's greater than 1. And probably I want to add an additional filter in here as well. Looking at the plot, so it's like less than 7.5. Okay, so I can see again, it does look potentially like the points where we do have yaw offsets, then it looks like the production might be slightly less than where we don't have a yaw offset applied. So to date, I'm just experimenting in this notebook, but the hope is that from this data set, we can identify the yaw offsets. In the previous challenges that were run, then lots of people were using machine learning. And in fact, machine learning resulted in the kind of best results for the challenges. So I thought I'd have a go here at just chucking the data in, since it's really quick and easy to do. So I split the data set so that we dropped the yaw offset angle from the X set of data, so what the data used to predict, and then in the Y I put in the yaw offset as the target variable, and then ran that through the prediction. Initially doesn't seem to have worked how I expected it to, because it's just a lot of noise, whereas what I want to see is something like this, where it's very clear what your offset is. And my expectation is this is all down to the data being very, very noisy. So if you were to take a single point from this spread and try and determine what the yaw offset was, you're not going to be able to. You need to do a lot more averaging to get to like sampling data together to understand what's going on during that period. So that didn't really work. And then the only other thing I started working on was, well, maybe I can just predict the power output and then see if the power output is slightly different when there's one offset or another, to see if it's of benefit having that yaw offset in the prediction of the power output. Yeah, that's as far as I got for now. And then I would be happy for others to have a go as well, and then we can work together to try and solve this problem.
Very interesting. Thank you so much for sharing.
Cool. Thank you, Jim.
Also wondering about like the background of this challenge, like what was the motivation and
Yeah, where did it all come from?
yeah.
Yeah. So actually, it's kind of a long-term project. It's gone through a few iterations. So within the open data exploration space, the first challenge we did was on doing an operational energy yield assessment. So trying to predict from a wind farm with several turbines, or in fact, two wind farms with several turbines each, what the long-term generation was going to be from those sites. So that was challenge number one. The second challenge was actually to try and determine the static yaw misalignments on those turbines. The problem was we had no ground truth. So with those turbines, we could run analysis, but then we could come up with different numbers each, and we didn't know whose numbers were right and whose numbers were incorrect. So there was no like ground truth to say, yes, turbine 6 is misaligned by 6 degrees, because one party would be like, no, it's misaligned by 2 degrees, and another's like, no, I think it's 10 degrees or minus 10 degrees. And there was no like proof to say who's right and what methodology is actually working. From that, we identified what the problem was, or one of the key problems was that the wind speed measurement on the turbines, which we were using to try and identify static yaw misalignments, is actually influenced by the misalignment of the machine. So what that means is the variable you're trying to use to determine the misalignment is actually influenced by the misalignment itself, which led you in a like circular argument. So you couldn't be sure whether you were improving production or you were just changing how the data looked, basically. So we ran a challenge to try and like discard that variable. So what we did, we had one target turbine where we wanted to know what the power output was, and we only used data from the other 5 turbines on the site to try and predict the power. What we found out was that the machine learning algorithms were very good at predicting the power, and in fact, so good that they were actually recognizing where that turbine had a misalignment. And so we didn't actually solve the problem we were hoping to get an independent measurement because actually there had been some leakage effectively in the data set.
So
So
you use like four other data from the data set from the four other turbines to predict another turbine, but then
yep,
it became somehow like perfect. You were able to get the perfect measurements.
yep,
Okay.
yeah. The prediction was too good to use because it was like somehow identifying these misalignments
How
despite
did that
not
work?
giving that signal to the turbines.
What
So
happened there? What happened?
So I think what it was basically there's a correlation between your target turbine and the other turbines.
Yeah.
So as the width, this is like a physical reasoning, but not necessarily the like truth. This is how I reason it. It's like if you've got all your turbines pointing into
Yeah.
the wind moves slightly,
Yeah.
all the turbines at the same time experience that same misalignment
Aerodynamic.
appearing.
Yeah.
Yeah. And that means it's not like the turbines aren't fully independent when you're comparing
No.
those metrics. They
Yeah.
are connected. And it's
Yeah.
like,
There's definitely the correlation. There's a correlation. Okay, that's an interesting finding.
yeah, yeah, it was. And I was shocked when I saw the result because I was like, how has this happened? Like, how does it know what's like the misalignment of this turbine? We've not given it the misalignment from this turbine. It still seems to.
But then are they the same, actually same manufacturer, so the same exact same turbine and even like very close location, just right next to each other?
Yeah, yeah,
Okay. Very
yeah.
interesting. Okay.
Yeah, it was a quite interesting result. Yeah. So then this challenge has come out of that because we've said, okay, well, we tried to do the challenge originally without a ground truth. We then thought, oh, it's okay, we'll solve this through like a clever predictor of the power output, which will be independent of that turbine that you're looking at. Then it turns out it's not. And then we're like, okay, well, we've got this test turbine. Let's apply the misalignment and we'll have a ground truth and we know what it is. And then we can use the data to try and identify that misalignment that we've applied.
Hmm.
So
Okay.
that's how this challenge has come about.
Okay.
And I should say within the industry, then there are various companies that will sell you a solution for this problem. So there are hardware solutions where you install a LiDAR or you install a like device on the nose cone of the turbines to measure the wind independently. And there are companies that will say we can determine this from SCADA data.
Hmm.
So in theory, the industry has got a solution to this. It's just not an open solution.
Hmm.
Um, and plus, with those SCADA analyses, then it's not necessarily a validated solution either, because there's always this risk that maybe they're doing the same mistake that we did in
Right.
our challenge, that they
Right.
think they're improving the generation, but
Right.
actually all they're doing is improving the way the data looks, not the actual generation from the turbine.
Right. Yeah.
Um, so yeah, hopefully with this challenge, then we can have a open solution that can be used by everyone, and we have it validated, at least on this test turbine, to say it's feasible to do this
Hmm.
using the data.
Okay. Very interesting.
Yeah.
I think another question I have is that so you mentioned about like these LiDAR data and things like that, right? Like have you like let's say if you purchase this LiDAR data, do you typically look at them together with your SCADA data?
Yeah, yeah. So there's like the LiDAR data can be used independently. So you can just be like, okay, well, all I want to do is measure the relative wind direction. And
Yeah.
if it's not zero, then there's an offset and I'll do a correction to that. So I'll be like, oh, I've measured a 5-degree offset on average. So now that I've measured that, I'll correct my turbine by 5 degrees and things will be great.
Yeah.
So that's one way of doing it. But I do think there's value in combining it with the SCADA data because effectively the objective here is not to get to a zero misalignment necessarily. The goal is to maximize generation from your turbine.
Yeah.
And so to do that, what you want to do is combine like LiDAR data with generation data
Mm.
and maybe some other signals and say this is the angle where you maximize production.
Mm. Yeah,
So for
but theoretically, like when the offset is zero, then that's when you maximize your production. You just don't know if this theoretically is correct because you don't know if the like even the measurement is correct. Is that like kind of the theory?
yeah, well, it's also well, in general, yes. Like, but zero is not actually necessarily the perfect angle with some
Ah,
turbines.
right. Okay. Okay.
Yeah,
Okay, so then theoretically, like when people design these turbines, they're like, okay, when it's perfectly aligned, then you should have your maximum wind. But then in practice, people observe saying that actually you don't have to always align perfectly with the wind direction. If you offset a little bit, maybe for your particular design of the turbine, it's actually
it's
beneficial for you.
better. Yeah, yeah,
Okay,
that's it.
okay.
Yeah, yeah. And this is particularly true for when you're using the measurement that's on the like behind the rotor on the back of the
Mm,
nacelle, because the rotor's rotating one way and your wake coming off the rotor is doing something. It's like moving around the turbine, so it's not flowing uniformly in nice straight lines backwards. It's like
mm,
flowing around to the side, and so the wind speed or wind direction sensor, when the turbine is pointing directly into the wind, is actually measuring a slight offset because it's like waked on one side more than the other. Um,
mm,
and so your sensor measurements might say like it physically says 5 degrees, but that's just because the wind has moved round
yeah,
behind the rotor.
yeah,
Um,
very interesting.
it's one of those problems. What I like about this problem is it's like super simple initially, and then the more you think about it, the more you're like, that makes it a bit harder. It's like so it should be very simple. You just like check what the misalignment is, check what the power is, and you're like, okay, that maximizes power, fantastic. But then you're like, well, actually, the wind speed's constantly changing, the wind direction's constantly changing. The measurement is influenced by these two things and the like misalignment of the turbine. So it actually makes it very hard to do this in practice. Whereas,
Mm.
if you have a if you have a turbine simulation on a computer, it's very easy to solve this problem.
That's what I'm wondering if someone has or if or if your company has this aerodynamic model and the simulation model that we can just utilize.
Utilize and play with. Yeah. So I don't think we have a model of this turbine setup. Uh, Maybe we can check with someone at the university. But there are open models that you can use. So
Mm,
like um, if you've heard of OpenFast, that's a turbine simulation software.
mm,
Uh, and that one has a set of turbines that are already there as templates. Uh,
mm,
so we could set this turbine up in that system too,
mm.
uh, and have
Yeah,
a play. Yeah.
that might be interesting. I'll take a look at this.
Okay. Any other questions from the group? We've got 5 minutes to go. So
Hey, this is Ganesh. Thanks for walk through whatever you are doing. I think this is very helpful.
yeah, no
Maybe
worries.
it's like person like me. I'm very new to analytics field. Maybe I guided team when I was in GE, but I never did something on my hands-on. So I think this will be good opportunity for me to learn the hands-on thing.
Yep. Yeah, I think it's good. And this is quite, from my point of view, quite a nice data set. It is like it's only one turbine, so it keeps things fairly simple, but it's quite interesting because it's got higher frequency data that you wouldn't normally access or have access to. And we've applied something to the turbines that we should be able to hopefully identify. So it's like solving a real world problem that could benefit the industry if we manage to solve it.
Yeah. So one last thing that I have is, can I connect with someone from this group and work with them, or I have to work individually on my own?
Yeah, no, teams are welcome, and yeah, I mean, I'm happy to have a couple of calls with you if you want, and we can work together. Or if there's someone else in the team, uh, happy for you to connect with them too.
Yeah, I
Okay.
think I will just drop my email account. And then happy to connect with anyone who wants to chat. I think especially Ganesh, if you want to chat about the mechanical side, I'm very interested to hear about your perspective as well.
Sure. Thank you.
Cool. And then the other thing I would encourage is using the WeDoWind platform. So just very quickly share again.
Yeah, I put some links already. The first one that I sent is for designer.
Okay, yeah. So on this platform, we've got the challenge description. We've got the events where you find the invite for this call, and then we've got another in January, February, and March set up to discuss this challenge. So they're there. And then we also have a feed where you can like post questions or answer other people's questions and also chat. I mean, chat and feed seem very similar to me. But effectively, if you want to share something with the group or you found something interesting or you've got a question, those are good places to put those. And then everyone can see the answers or discussion. And then also you have the ability to chat with people as well within the WeDoWind ecosystem. Cool. Okay, but yeah, so I'll let people go, and there'll be another call, yeah, in a month's time, which will be after Christmas and the New Year. So I wish you all a great Christmas and New Year if I don't speak to you or see you beforehand. Thanks for joining the call.
Thank you. Bye.
Thank you. Bye-bye.
Thank you.
Thank
Bye.
you. Bye.
Thank you. Bye.
Thank you. Thank you, everyone. Bye.